Those are the homework assignments. I mean, you see, well, you can see, but shock waves occur only in supersonic flow. Like we said, if you have subsonic flow, the gas molecules can sense the signal, can sense, for example, the presence of an object, and so on, right? So it has to be supersonic because the gas molecules will be moving so fast that it would not recognize the signal, it would not receive the signal until the gas molecule hit the source of the signal. Right? So we already gave you an example that if you have a supersonic ambulance, it's probably self-defeating because the ambulance coming with supersonic speed and it gives you the desired sonic speed. So in a sense, the ambulance is running ahead of its own signal. Right? It's so interesting that, let's say, if you can run supersonically, you don't even hear yourself. Your voice is separate. You don't even know your voice is not. That's really bizarre, right? But of course, we all like to be supersonic. We don't just want to be sonic. But sonic is already very good, right? You better be okay, sonic. Supersonic will be even better, right? But you definitely leave your enemies behind. It's good, right? Okay, so it has to be supersonic. So you have to think signaling mechanism that we have talking about, right? Now, normal shock waves, what we are saying is this is shock wave, normal to the flow. That's what we're doing, right? So you have something coming as an M1 greater than 1, because it has to be supersonic. So the flow comes with M2. If this is region 1, this is region 2, M2 will be less than 1. That's what we have. Now, we want to consider 1D also. 1D. The flow is uniform everywhere. Okay? And the flow is isentropic upstream and is isentropic downstream. But here it's non-isentropic. Think about normal shock wave or the shock wave as a compression process that occurs so fast, irreversible. So even though shock wave is very thin, usually how thin it would be? It would be about a few mean free path. About a mean free path. You probably have your chemistry, so you know what mean free path means. Mean free path means the distance traveled by a molecule between two collisions. Okay, there are all the molecules in here, they collide. So let's say, boom, and it travels some distance and it hits the other. That distance, on average, that is usually on the order of submicron. Okay, so most shock waves are on the order of micron. The higher the number is, the thinner it is. So that's the case. Now, how would this form? You need to consider mass conservation. You need to consider momentum conservation. You need to consider energy conservation. So this is nice. If I can tell you one thing, you as an engineer, everything you learn goes down to these three equations. Well, it takes you 4 years, right? So you need to think this is really important. No matter what you think in the future, even outside gas dynamics, high speed air, when you don't when at first sight you don't have any clue on how to solve the problem, think about these three things. Nothing escapes from this law of mass conservation. In your fluid mechanics and gas dynamics, anything that flows is called continuity, right? Momentum conservation is really Newton's second law for gas flow or fluid mechanics. So you have the control volume approach, right? So you have ddt, three-point integration over control volume, and the flux going through the control surface. Just think about that term. If someone gives you a device and says flow coming, think about these three things. If it's steady flow, mass coming in should be equal to mass going out. If it's unsteady flow, the difference is what's accumulated in there, what is being depleted from there, right? And if the momentum comes in and momentum goes out are different, then there must be some force exercised on the fluid or on the gas. And then reaction force will be on that device. Right? So you start thinking about this, you will be able to find some clue on what they should be. Right? So always think about it. Now, let's talk about the formation of shock. Let's say if you have a long tube, very long tube, this is the exaggeration, okay? It's very long. Now, if I have a piston, this drawing is actually in place. If I have a piston and I give it a push, it goes from either 0 or some already known velocity, and you give it an extra velocity. Let's say very small, dV. It forms the wave. So let's say at one moment, you see a wave here, and you see another wave here. Okay. Let's say here the state is called 0. So you have here rho 0, t0, p0, so on and so forth. And you also have a speed of sound called a0. A0 is equal to gamma r t0. Okay. And here, let's call this state 1. So here, rho 1, p1, t1, a1 equal to square root gamma r t1. And then you have state 2 here. So p2, t2, rho 2, a2 equal to square root of gamma r t2. Now here, v0 is equal to 0. There is a V1 not equal to 0, and then there's a V2. Because you keep pushing it, the gas behind ahead of the piston would have to move with some speed, right? But one very important thing to think about is that because this motion really amounts to compression, so the temperature here is slightly higher than temperature there. Make sense? And the temperature here is, again, higher than that. So the first wave, if you can discretize the wave, the first wave will be traveling at this speed, because this is a small disturbance. We're talking about very small change, right? So this will be traveling at this speed. This wave, because it's traveling into this gas, and this gas has a P of some square root of gamma. So, because it's a compression, the wave will pile up. The waves will pile up, right? So let's say this is T equal to T1, and after several, of course now I'm leaving this far behind here now. Right? These waves cannot pile up. I'm not saying that this is the same location, okay? This very long tube, so some moment later we are looking at here, right? We are looking at what's going on here. I move it here, right? So you have this. T equal to T2. Even later, you will have T equal to T3. All the way collapsed. So, what happened is, because your later wave has a higher speed, right, than the earlier wave. So what will happen is that because it's compression, you can say, now, T equal to T1, you have that pressure like that, right? Let's say this is X. T equal to T2, you have, let me just put this X back here, it's not going to do it. T equal to T3. And temperature, of course, will be similar because compression, right? Compression means what? The piston is doing work on the gas. The gas is receiving work, the temperature should go up, right? And initially, you can think about it being isentropic, then the temperature going up and pressure going up will follow some isentropic relation. But once the shock wave occurs, it's definitely not isentropic, right? Or if your pushing is very fast, it's not quite isentropic. So what we are concerned here is the shock wave. Given that when you compress it very fast, it's not isentropic, that we already know. But how non-isentropic it is really is difficult to measure, right? But if we have a shock wave, we definitely will be able to tackle it because it's very definite, right? Very definite. So this is what we call shock wave. Now, your temperature will be similar. The temperature change probably is smaller, if you can draw it. The temperature also goes through a jump. But this jump, again, as I said, it occurs over a few mean free paths. That's usually on the order of microns. Maybe just 1 micron, or even less. So you can consider shock wave as a mathematical discontinuity. Right? Remember from the calculus, if you are asked to find a slope, give a function like that, you can take slopes anyway. But if it's like this, the slope is infinity, right? Because the change, delta P over delta X, that delta X is so small, it's like 0, then you have infinity. And infinity is non-existent, right? So mathematically, when you encounter something infinity, you say it's non-existent. So it's a mathematical discontinuity, and we assume that it's very thin. And we assume to be mathematical discontinuity. And again, the reason you will experience shock is because you are not prepared for it, right? So this is kind of very similar to our everyday language. Or shocking means, well, if all your experience is subsonic, this will never happen, right? That's why it's shocking means it's a shock, right? So in your regular everyday life, things goes, may not be what you like, but slowly, right? Or something like shocking news, right? So you start, under normal circumstances, that will not happen. Because normal circumstances will be subsonic, right? So under normal circumstances, you would not imagine that a flow can accelerate in a divergent channel, right? So it's the same thing here, right? Because it's a supersonic flow, a lot of things are not what you would think would happen under subsonic conditions, including shock waves. Okay. So there is this overtaking process, right? The later wave overtaking the earlier wave. That's when you have shock wave. Now, if it's an expansion wave, for the sake of discussion, expansion. cylinder away from the gas. Of course, if this is infinite, it will be compression wave on this side, right? But let's look at this side. It will be expansion. So you have a, let's say this is one earlier shock wave, one earlier wave, because this is a small disturbance. And then there's one here, there's one here. So this is T1. But then at T2, or later on, T2 greater than T1, let's say, you have. Why? Because of the expansion, if this is T0, this is T1 will be less than T0, this will be T2 less than T1, this is T3 less than T2. So you have A3 less than A2, A2 less than A1, A1 less than A0. So even if you are pulling the piston, in this case, to the left, to your left, the signal still propagates to the right. Okay, this, I want to emphasize this because sometimes they want, if you pull left, shouldn't everything goes with you to the left? Which is true, the gas will go with you to the left. But the signal goes that way. But you just imagine if my voice propagates to you, apparently my vocal cord vibrates, right? My vocal cord cannot just keep pushing, right? The energy come out of my mouth, right? Apparently it goes like this only, right? Make sense? And if you think that, well, when my vocal cord retracts, you will not hear it, then you probably will learn half the gas dynamics, not the whole gas dynamics. The other half of the dynamics you couldn't hear, right? So apparently even when it retracts, it still gives you a signal. The signal is that the pressure is becoming lower, right? And the temperature is becoming lower. And if temperature is becoming lower, that means the subsequent waves will travel at a lower speed. So the spacing between the waves is getting larger and larger, so there will be no shock wave. So there is no such thing called expansion shock. Right? There's a question there. Yes.
Sound pressure waves travel equally in all directions, right?
Well, in this case, in one direction only because you are in the tube.
Okay.
So we use this as an example.
So in the real world, you wouldn't have that hemispherical shock. It would be a shock in all directions, right?
Real world. The tube is real world too. It depends on the question, right? If you are dealing with our Dr. Subi about 2 years using shock tube to do his research. Very real, right? So it depends on your question. Similarly, some question is one-dimensional, some question are two-dimensional, right? Yes.
Would there still be waves to the left of the piston as well?
Yeah. Then to the piston,
Would be the same case for the first piston?
it's really this case, leave it out. Because we are concentrating on what's to the right? That's why I need to do it twice. Otherwise, I can throw everything in one. Yes.
So left of the piston is a vacuum. What would happen if the piston just moved as fast as the speed of sound, so faster than the speed of sound? Say the piston moving supersonic. What would happen to the pressure?
The sound wave is never supersonic. The sound wave is always sonic.
The piston is moving supersonic. What would happen with the gas on the right-hand side of the piston? If the piston is moving supersonic, what would happen to the gas on the right-hand side of the piston, since it will never have a shock wave?
And shock wave already occurred. If piston is moving supersonic, shock wave already occurred.
There's no such thing as an expansion shock wave. So what would happen to the gas? It would just keep expanding infinitely?
No, for example, if I'm pulling this piston to your left, let's say initially it's not moving, right? Let's say I give it dV. And that's dV. This is velocity. So that signal, the fact that it's moving, give out the signal. The signal is an expansion signal, and the signal travels at speed of sound. But your question would be like, well, what happens if I move it supersonically? Well, there is a limiting condition where you pull it so hard, you actually create a vacuum. If that vacuum happens, there will be no signal, which is true. But under most conditions, the reasonable speed, what we are talking about here is not whether the piston is moving at supersonic speed or not. I would prefer that you can just restrict it to subsonic, because what's important is that the velocity changes, and that sends out a signal. Now, if your piston is already moving supersonic, shock wave already occurred. We are talking about shock formation, right? How would a shock form? It's because your later wave catch up on your earlier waves. And expansion is that your earlier wave gets further and your later wave gets further and further away from the previous wave. So it kind of smooths out the thing. You and I have expansion shock.
So then if this, like say it was in like an open air, like an aircraft, no shocks would form on the tail end, essentially propagating in the opposite direction it was traveling for that reason. Would that be correct, or is that totally different?
Let me modify your question so that I can answer it. Let's say if you have an aircraft, I just be very quick and show an aircraft. Not anymore. Okay, let's say this is red. If it's moving subsonic speed, there will be no shock wave. If it's moving supersonic speed, then there could be shock wave. For example, there could be oblique shock wave. And there could be oblique shock wave here also. So if you said that while in tail end nothing would happen, so I don't know exactly what you are saying. Now, if you have a projectile, let's say, that would be simpler, right? So if you have a, let's say like a bullet, right? So what happened here? It's a wave, what we call wave, right? This question is very different from that kind of question. Because of course, in a way, your pressure is lower, which is true, right? But that wave may also, that signal may also propagate. Now, of course, as you said, it probably will propagate more like a spherical wave rather than a plane wave, right? But if it's moving supersonic, then you are right. There will be shock wave, or most likely a big shock wave, because your projectile usually will not have a very blunt nose. You wanted to have a very slender nose, right? So you probably have a big shock wave. Now, if it's moving supersonic, well, I don't know how to answer, because when you are talking about projectile, the flow field is very complicated. That's why conceptually, when we are talking about shock wave, we like to use long tube, because that gives you the physics, right? So in 3 dimensions, the physics still holds. Now it's just more complicated. Make sense? Okay. Now, so remember, there is shock wave, and there is no expansion shock wave, right? Okay. Now, the next thing we want to talk about is, you recall, P plus rho v squared is equal to constant. Right? This is momentum equation. Remember this? You take a derivative, dp plus, oh, I'm sorry, 1/2 rho v squared. Right? No, rho v squared. 1/2 becomes the energy, right? So rho v squared, pressure plus momentum flux, because it's v times rho v. Rho v is the mass flow rate. Mass flow rate times v, the momentum flux. And you take a derivative, it becomes rho v dv equal to 0. Now how can you say, well, if you take a derivative, you have 2. But you remember, rho v is equal to constant. That's mass flow rate, right? That's mass. Rho v equal to constant. So you can have rho v times v, and you put a bracket here, and you take a d, because this is constant, you can pull out. So this is going to rho v times dv. Right? So for compression, dp is greater than 0. That means dv is greater than 0. For expansion, dp less than 0, dv less than 0. So, if you take this direction of x, that's exactly what it means, right? Because your dv is positive, your dp is positive. And if you take an expansion like this, your dv is negative, your dp is negative.